In all of my variation videos so far, what I've been doing is I've been working with population values. So let me show you what I mean by that. When we worked out deviations, a deviation was said to be x minus the population mean. It's the difference between a score and the population mean, showing you how far an individual score is from the expected population mean. And then when I found my sum of squared deviations, all that we were doing there was just summing up those deviations. So again, I'm using the population mean. We then carried on to find the variance. Let's see, variance. The variance was written as sigma squared, and this is the sum of squares over the population size. And then finally, my standard deviation. Standard deviation. That's sigma, and it was just the root of the variance. Okay, so this is all population stuff. Now, what I've said, though, throughout the course so far is that typically what you'll see is that we don't usually work directly with population data. Instead, in statistical research, you're forced to be happy with, or you're forced to be satisfied working with samples only. We're going to use samples to take the place of populations, because populations are often difficult to observe directly. We usually don't have the resources to effectively measure or record all of the data in a population. So I'm going to need to have some counterparts to each one of these, to the deviation, the sum of squares, and the variance, and the standard deviation. I'm going to need to know how to deal with them when I'm working with sample data. Now, it's not a big deal. Most of it's almost exactly the same thing. For example, a deviation is written as, let me put the label again, a deviation is just x minus the mean, but now I'm going to be dealing with the population, or sorry, the sample mean. That is a capital M. Not a big deal. It's still the same formula. It was x minus the mean. It's now x minus the mean. I just have to use the appropriate mean. If I have a sample, I'm using the sample mean. Sum of squares is basically the same idea. My sum of squares is still going to be the sum of my squared deviations, but of course we've just defined the sample standard deviation, or sorry, the sample deviation as being x minus the sample mean. So really nothing new here. It's the same formula. I'm just using a different symbol to show the population mean and the sample mean. Now it's when we get to the variance that we have an actual change. And it looks like this. First of all, I'll write out the formula for variance. We have a different symbol, s squared instead of sigma squared. That shows me if I was reading a paper, a research paper, I would see s squared and I would know that they got the data from a sample. They got this calculation from a sample, not from the population. It's still sum of squares. At the numerator, the top of the fraction, is still the sum of squares, but the denominator is not what you would expect. I would expect it to just be the sample size instead of the population size, but it's a bit different. It's the sample size minus 1. And this is an important distinction. Now we don't just have a different symbol to show I'm dealing with sample data. We actually have a different formula. We actually have like different mathematics going on here. And so what's up with that? Why would I do something like that? Why are we changing the whole idea around? Remember, we were trying with a variance and then a standard deviation to get an average. And an average means you're summing something up and you're dividing by the number of things that went into the sum. So why would I divide by one less thing? Why would I take 1 away from n in my denominator? Well, Mathematically, what happens if you take 1 away from the denominator is you make the whole fraction worth more. Think about it like this. Let's say you've got 10 over 5. What's that equals to? That's 10 over 5 is 2. But what if you took 1 away from the denominator, just like we're doing up here? So take 1 away from 5, you get 4. Well, now it's not going to be worth 2 anymore. It's going to be worth 2.5. You've increased the value of your answer just by taking 1 away from the denominator. In fact, let me just make sure I've got my math right here. That's a 25% increase, going from 2 to 2.5. It's a sizable increase when you've taken 1 away from your denominator. So why would I do that? What's going on with that? Well, to make sense of it, let me make a bit of space here. Okay, so the whole idea is this. In statistics, we want to be able to describe a population, but we don't have the population accessible to us. Instead, we have to make do with simply collecting sample data, and we have to hope that the sample will fill in that job. It will represent the population. But that's not a certainty. It's not necessarily going to do that. Imagine you're looking at your university, and you're looking at the ages of students at the university. Most students at a university are going to be like 19. It's going to be a bunch of 19-year-olds in any typical group, 20-year-olds, 21-year-olds, and all the way up to like 22, 23, 24, and so on. So if you had any group of just randomly selected people, you could find this sort of a thing. However, there are many people who start university early for one reason or another. They're able to fast track through high school. So you might have somebody who is 18 or 17, or you might even get a 16-year-old, like some child prodigy that really got to university very fast. As well, undergraduates are not everybody at university. People take master's degrees. People take PhDs. You have postdocs. So you could get somebody who's 28 or somebody who's 32 at the university. In fact, I think that they offer free education or free university admission to people who are senior citizens. So you could have somebody who's 82, forget about 32. You could have somebody who's a senior citizen. But these people, the 16-year-old and the 82-year-old, they're going to be rare. It's not very likely that if you took a small sample, like let's say instead of being able to look at the entire population and measure the entire population, what if you had to be satisfied with just taking a small sample? Maybe you only have time for a survey that includes just a few people that you speak to outside of your class one day. And so you probably get a typical group of people who are 19, 20, 21-year-old. Now, your sample doesn't include all of these extremes, and so the sample variation is smaller than the population variation. Or more simply put, sample variation is too small. It's too small because it's difficult for a small sample to include as much variation as you would find in a larger population. So what can we do about that? If we know that there's that problem, that it's too small, well, we can easily correct for that. Let's go back up and have a look at what's going on in this fraction. When we reduce the size of the denominator, what you do when you reduce the size of the denominator is you increase the value of your answer. So that's exactly what's happening here. By taking 1 away from the denominator, from having n minus 1 instead of n, we're taking this value, the sample variance, and we're boosting it up. We're giving it an artificial boost because we know it's probably going to be too small if we simply just said that s squared was equals to sum of squares over n. If we just tried to follow this formula but applied sample data or used sample data to fill it out. It would be too small. So instead, we do this. We give it that extra boost. Now our sample variance will do a good job of properly representing how much variation there is in the whole population. It gets a bit more complicated than this. It might seem that that's a pretty amazing fix, just subtracting 1 and that takes care of everything. But it's pretty interesting if you think about it. Like if you had a small sample, like if we have a sample of only 5 individuals, we got a 25% increase by taking that 1 away. What if our sample was really large? Well, really large samples probably do a good job of showing how much variation there is in the population. So if you had a sample size of 100, for example, your answer would come out here to be 0.10. That's probably very close to the actual amount of variation in the population because your sample size is so large. It's not a poorly representative sample. Larger samples are good at representing the population. So you wouldn't need much of a correction. Well, taking 1 away doesn't mean much when you had a large number like 100. When you work this out, 10 over 99 is equals to 0.101. This is, actually it's 101010 and so on. This is a very small increase. This is only a 1% increase going from here to here. Here it was a 25% increase. So it's kind of a cool little correction that makes a big correction for small unrepresentative samples, and it makes a small correction for large samples, where the correction is not really needed very much. After this, things are easy again. The standard deviation, it's just the same as what you would expect. S for standard deviation instead of sigma, just like we did S squared instead of sigma squared, it's just equals to the root of the variance. And so we've got our list here for populations and samples. There was only one real difference that happens here at the variance. And the reason that we're doing that, the reason we make that n-1 at the bottom, is just to help boost our variation as we measure it in a sample because it's often too low.